This is part 2 for our video where we are attempting to find a relationship between the beta integral function and the gamma integral function. Remember, the playlist for all the videos is at the website digital-university.org. Okay, in the first part of the video we ended up with this expression: m factorial times n factorial was this double integral where everything's expressed now in terms of polar coordinates. So we have e to the minus r squared, then we have r to the 2m plus 1 power, r to the 2n plus 1 power, times r dr. R goes from 0 to infinity, and then we have the cosine of theta to the 2m plus 1 power, the sine of theta to the 2n plus 1 power, d theta, and theta goes from 0 to pi over 2. So if we multiply these r's together, that's the same thing as adding exponents. So we'll have 2m plus 2n plus 1 plus 1 plus 1 plus b to the plus 3 power then. E to the minus r squared dr, and this is going to be the same. Now, we want to do one more variable change. Notice that here we have e to the minus r squared. Well, let's do it like this then. Say let, and the reason why we want to is, notice what we have. We have r raised to a power, then e to the minus r squared dr. Well, if it was like this, r raised to some power, and if we had e to the minus r dr with this integral here, then that would start to resemble a gamma function. We've got this r squared term in here. So we're going to try and do a substitution and see, once you go through all the steps, if this might resemble then a gamma function. So we say let r squared equal rho, then 2r dr, that equals d rho. We want to know what is dr going to equal, so dr, that is 1 over 2 times r d rho, but r is rho to the 1/2. So this would equal 1/2 rho to the minus 1/2 d rho. So there's our substitution for dr. So we're going to work with this integral here. So we have, in fact, let's just rewrite it. 4 integral from 0 to infinity r 2m plus 2n plus 3 e to the minus r squared dr. Now we make the substitution. R we roll to the 1/2, so we're going to roll to the 1/2 to this exponent 2m plus 2n plus 3 e to the minus r squared, that is e to the minus rho, and then dr is this. So we have 4 with the 1/2 out here, rho to the minus 1/2 d rho, rho to the minus 1/2 d rho. Now r goes from 0 to infinity, so clearly rho also goes from 0 to infinity. So this is equal to, this is 2, 0 to infinity. Here we have rho to the 1/2 to this power, so that's going to be rho. Well, here we have rho to the minus 1/2. Then here, rho to the 1/2 raised to this power, so that's going to be m plus n plus 3/2 e to the minus rho d rho. Now multiplying these two rows together, that's the same thing as adding exponents. So we have rho to the m plus n plus 3/2 minus 1/2. Well, 3/2 minus 1/2 are just 1. So this is rho to the m plus n plus 1. When you multiply these together. So let's replace this with this. So we have rho to the m plus n plus 1, and then e to the minus rho d rho. Okay, so our strategy worked, it looks like, because we started off with this expression, e to the minus r squared dr, r raised to some power, but now when we did this substitution, look what we have. E to the minus rho d rho, rho raised to some power, and this then indeed is a gamma integral. Recall what the basic definition is, that gamma n, say, that is equal to this integral x to the n minus 1 e to the minus x dx. X goes from 0 to infinity. So when and this integral is in the same form, e to the minus rho d rho, rho is raised to some power. Now, the way our relationship works is that the exponent of this plus 1 is the variable here for rho. So here then, this would be, we have a 2. Don't want to forget that. But for the integral here then, that would be the gamma function of this exponent plus 1. So that would be m plus n plus 2. That's what this integral is. So once we made this substitution, then this becomes a gamma function integral. Specifically, we had a 4 here. Now, because of the 1/2, the 4 becomes a 2, but we have 2 times the gamma function of m plus n plus 2 after we did this substitution. So let's rewrite our equation for m factorial times n factorial, where we replace this with 2 times the gamma function of m plus n plus 2. Of course, this resulted because of our substitution here. So what we have then, let's make some room. M factorial times n factorial equals 2 times the gamma function of m plus n plus 2. And then we still have this integral. fact, let's take this 2 and put it here. 2 times this integral, 0 to pi over 2, and then we have the sine of theta to the 2n plus 1 times the cosine of theta to the 2m plus 1 d theta. And theta goes from 0 to pi over 2. Okay, now remember from our work with the gamma function that the gamma function of, say, n plus 1 is equal to the factorial of this here minus 1. So that's just n factorial. So the gamma function of m plus n plus 2 that would be m plus n plus 1 factorial. So we're going to replace this with this up here. M plus n plus 1 factorial. And again, this kind of stuff we had done in the previous integrals when we were working with the gamma integral function. Now, let's take a look at this integral, because this looks like it ought to be a beta integral function. Let's remember now, let's just take this away for a moment. Here was our definition of the beta function when it was in a trigonometric form. This is the beta function of mn. Well, suppose we want to find the beta function of m plus 1, n plus 1. So this m here gets replaced with m plus 1. So we'd have the exponent of the sine term would be 2, where the m was replaced with m plus 1, then we have minus 1. So this is 2m plus 2 minus 1, or that's 2m plus 1. So when we have the beta function of m plus 1, the exponent on the sine term is 2m plus 1. And likewise, for the cosine term, it's going to be the same thing, n plus 1. Well, the exponent of the cosine term is now going to be 2n plus 1, because this n gets replaced with n plus 1. Just like we did with the m, it's the same thing. So the beta function of m plus 1, n plus 1 is this integral right here. Well, what we have from what we just did is we have this integral, sine of theta to the 2n plus 1, cosine of theta to the 2m plus 1. That's this. So this would be the beta function. Here we have n plus 1, m plus 1. This would be the beta function then of n plus 1, m plus 1. What we did was it's the same thing as this, except we switched the m's and n's around. Now remember that the beta function of mn is the same thing as the beta function of nm. So our integral here, this is the beta function of n1, n plus 1, m plus 1. But that's the same thing as the beta function of m plus 1, n plus 1. We had shown in a previous video that you can interchange the m's and the n's, and the beta function is unchanged. So beta of n plus 1, m plus 1, that's the same thing as the beta function of m plus 1, n plus 1. So this integral that we had derived, that is the beta function of m plus 1, n plus 1. Again, let's just review that quickly to make certain we didn't make it too confusing. Here is the beta function. The sign is to the m, has an m term in it. The cosine function has an n term in it, mn. Now if we have it for, say, not m, but m plus 1, then here this m gets replaced with m plus 1. So now the exponent on the sine term is going to be this, 2m plus 1. Likewise, the exponent on the cosine term will be 2n plus 1. So the beta function of m plus 1, n plus 1 is this, where the exponent on the sine term has an m, the exponent on the cosine term has an n. Well, the integral that we came up with is like this, where the m term, the sine theta, has an n up in its exponent, and the cosine has the m up in its exponent, reversed from what it is here. Well, this is just the definition then of beta n plus 1, m plus 1. But we had shown in a previous video that the beta of mn, the beta function of mn, that's the same as the beta function of nm. So that means then that this right here, which is equal to the beta function of n plus 1, m plus 1, or we could say m plus 1, n plus 1, since they're the same thing. So what that means is that this integral right here is beta m plus 1 n plus 1. So what we have is beta m plus 1 n plus 1 times this equals this, or equivalently what we can say obviously is that beta m plus 1 n plus 1 equals m factorial times n factorial divided by this. Or, to write this now in terms of gamma functions, remember m factorial, that's just the gamma function of m plus 1. That's the gamma function of n plus 1. This would be the gamma function of m plus n plus 2. Add 1 to this expression. M plus n plus 2. Well, for this, let's call this p, m plus 1, and n plus 1, let's call that q. So we can say that the beta function of pq, that will equal, this is p now, this is q, and if we have p plus q, that would be m plus n plus 2, which is what this is. Put that in better focus. Finally, there it is. This is what we've been trying to derive. The beta function, say, of pq is equal to the gamma function of p times the gamma function of q divided by the gamma function of p plus q. And again, all we did right here was just do a variable substitution. m plus 1, call that p, n plus 1, call that q. So beta pq, this is now the gamma function of p, that's the gamma function of q. And notice if we add p plus q, that is, if we add p plus q, that's m plus n plus 2, which is what this is. So this is p plus q. There it is, finally. That's what we've been trying to derive. Sorry it took so long, but hopefully it was worthwhile. We kind of wanted to do it step by step because this is a very important relation. And we will use it in future videos when we're trying to solve specific problems.